and varies directly as the product of their masses. Mathematically, we can write that great law down in the formula some kind of a constant multiplied by the product of two masses divided by the square of the distance. F equals g(m)m prime over r squared. Now, if I add the remark that a body reacts to a force by accelerating, or by changing its velocity every second to an extent inversely as its mass, or that it changes its velocity more if the mass is lower, inversely as the mass, then I have said everything about the law of gravitation that needs to be said. Everything else is a mathematical consequence of those two things. Now I know that you are not all mathematicians, and you cannot immediately see all of the consequences of these two remarks. So what I would like to do here is to tell you briefly of the story of the discovery, what some of the consequences are, what effect this discovery had on the history of science, what kind of mysteries such a law entails, something about the refinements made by Einstein, and possibly the relation to the other laws of physics. The history of the thing, briefly, is this. The ancients first observed the way the planets seemed to move in the sky and concluded that they all, along with the Earth, went around the sun. This discovery was later made independently by Copernicus, after people had forgotten that it had already been made. Now, the next question that came up for study was, exactly how do they go around the sun? That is, with exactly what kind of motion? Do they go with the sun as the center of a circle, or do they go in some other kind of curve? How fast do they move? And so on. This discovery took longer to make. The times after Copernicus were times in which there were great debates about whether the planets in fact went around the sun along with the Earth, or whether the Earth was at the center of the universe, and so on. Then a man named Tycho Brahe evolved a way of answering the question. He thought that it might perhaps be a good idea to look very, very carefully and to record exactly where the planets appear in the sky, and then the alternative theories might be distinguished from one another. This is the key of modern science, and it was the beginning of the true understanding of nature. This idea to look at the thing, to record the details, and to hope that in the information thus obtained might lie a clue to one or another theoretical interpretation. So Tycho, a rich man who owned an island near Copenhagen, outfitted his island with great brass circles and special observing positions, and recorded night after night the position of the planets. It is only through such hard work that we can find out anything. When all these data were collected, they came into the hands of Kepler, who then tried to analyze what kind of motion the planets made around the sun, and he did this by a method of trial and error. At one stage, he thought he had it. He figured out that they went round the sun in circles, with the sun off-center. Then Kepler noticed that one planet, I think it was Mars, was 8 minutes of arc off. And he decided this was too big for Tycho Brahe to have made an error, and that this was not the right answer. So because of the precision of the experiments, he was able to proceed to another trial, and ultimately found out 3 things. First, he found that the planets went in ellipses around the sun, with the sun as a focus. An ellipse is a curve all artists know because it is a foreshortened circle. Children also know, because someone told them, that if you put a ring on a piece of cord, anchored at each end, and then put a pencil in the ring, it will draw an ellipse. Figure 1. The 2 points, A and B, are the foci. The orbit of a planet around the sun is an ellipse with the sun at one focus. The next question is, in going around the ellipse, how does the planet go? Does it go faster when it is near the sun? Does it go slower when it is farther from the sun? Kepler found the answer to this, too. Figure 2. He found that if you put down the position of a planet at 2 times, separated by some definite period, let us say 3 weeks, then in another place on its orbit, 2 positions of the planet again separated by 3 weeks, and draw lines, technically called radius vectors, from the sun to the planet,